Okay, welcome back from lunch. Want to start on time here. So our next presentation, Introduction to GPU, will be from Dmitry Mikushin from Applied Parallel Computing.
Good afternoon, everyone, and welcome to the GPU computing workshop at the HPC Advisory Council Switzerland. My name is Dmitry. Besides Applied Parallel Computing, I also represent University of Lugano, where it's just here. You can find me in the lab building as a doctoral assistant. So today we will have a two parts session on GPU computing. The first will be general introduction, then two presentations on clustering tools, and then three presentations on programming models: Cuda, Cuda Fortran, MPI, and OpenACC. Okay, so let's start. And my first slide should be that well-known, obvious climbing teraflops chart, right? But I thought we should try to break this tradition and look into something that is not so obvious, not derived from the Moore's law. So what we had 6 years ago is CUDA programming technology for very limited amount of GPUs, and the need of expert knowledge or advanced research techniques to be familiar with GPU computing. 6 years passed since that, and now we can say that GPU computing is truly everywhere on the whole range, starting from the smartphones to largest clustering systems, and even such applications like automotive systems. Just to give you a range of, just an overview of GPU hardware. For instance, for smartphones, there is a K1 processor, which is a multi-core ARM processor with about 200 GPU cores on board. So you can actually do GPU computing on embedded devices, on unmanned aircrafts, on autonomous robots, and build up dense, energy-efficient data centers. The next level is mobile platforms like traditional laptops, where there are GeForce M GPUs, which are good enough for computer-aided design and engineering, and you see many of us you are using laptops for regular GPU applications development. The next level will be GPU workstations, where more massive and more broad simulations are possible. And also the key thing is the possibility to plug multiple GPUs into a single work node. The typical cluster node is also multiple CPU sockets composed together with multiple Tesla K20 passive GPUs. Which, in addition to desktop and workstation versions, offer such things like graphics virtualizations or remote GPU computing like Cuda that will be presented later. And maybe another interesting and emerging application of GPU computing is automotive systems, where also a kind of augmented reality can assist the driver and safety and provide entertainment. Okay, so GPUs are everywhere, which means that our course should teach you to program the whole range of devices. And the Cuda presentation that will be following this talk will apply to the whole range of these devices, which means that you can use almost the same program on mobile systems, and they will also work on large-scale clusters. So what is the position of GPUs in HPC systems? So here we have a node of Titan supercomputing. Here's the CPU undercover. Here's the host system memory. And here we have four GPUs. Maybe the key property for the introduction is that the GPU has its own DRAM, which means that either user or the software should explicitly transfer input and output data between the GPU and the host system. More schematic look on the same compute node will reveal that there are multiple CPU sockets combined with multiple GPUs. This is one of the possible setups. So here you see this is a so-called FAT node with 4 GPUs and 2 CPU sockets. Please note that depending on the I/O hub here, if we have one I/O hub or we have separate I/O hubs for each individual socket, our system may subdivide into two parts with slower interconnection, which means that with respect with GPUs and their host CPUs, we may have the near pair and the far pair, which is a NUMA system with respect to GPUs. So since GPU computing aims to be used in scientific research, it would be essential to make it play together with existing parallelism programming models. So, for instance, you can seamlessly use multiple GPUs in multiple processes, for instance, MPI processes. Moreover, you don't need the direct mapping of one process to one GPU. With help of MPI context underneath, it's possible to use multiple GPUs in a single process, or use one GPU in multiple processes. The same thing with threads. Threads can also be assigned to individual GPUs or multiple GPUs, and that means that either OpenMP programs or MPI plus OpenMP programs can play together with the GPUs, with multiple GPU systems. As I said, in terms of in internal technology, there are so-called GPU contexts, which could be switched from one thread to another thread, or from one process to another process, such that you can even reassign the GPU from one process to another. Okay. It has been a while since we start teaching GPU computing, and it turns that the GPU ecosystem evolves with time. So, for instance, in 2008 and several later years, we were teaching mostly Cuda, and we were limited with one family of GPUs. And now, GPU is actually becoming the technology for everyone, and we are no longer bound with Cuda, because a lot of free GPU-enabled libraries implement on all kinds of data processing. BLAS and Magma are for linear algebra, QSparse is for sparse linear algebra. MGX is linear solvers and multigrid. QFFT is FFT, and truss and cube are general data processing. Besides libraries, there are also directive-based languages that simplify GPU computing, like OpenACC and HMPP. OpenACC will be also presented today. And everything works already on 5 generations of GPUs, from very ancient, which are already not in general use, to the most recent, like Kepler and Maxwell. And it turns out that nowadays, Cuda is only needed to program something very specific or highly tuned. For anything else, you can just grab a library and have a solution maybe no more than in several hours, and the efficiency on GPUs will be quite reasonable. I will show you some examples. So, for instance, here we are benchmarking a BLAS double precision matrix multiplication. This chart represents GFLOPS for CPUs, actually 2 CPUs, for Xeon Phi and for Tesla K20. The performance gap here is about a little bit less than 5, right? So how it happens? So in case of CPU BLAS, we issue just one command. We call the BLAS function. It is the same for GPUs using the QBLAS library, except that we also need to provide the data transfer mechanism. We need to allocate memory on GPUs. We need to transfer input matrices, and transfer back the output matrices. We also create a handle for BLAS operations, which is meant to be for multi-GPUing. Set matrix is copy operation from host to device, and get matrix is copy operation from device to host. And afterwards, we free the GPU memory. The cool thing is actually that was a old classic GPU approach. Starting from Cuda 6.0, there will be no need to provide those explicit memory transfers, because the new NVBLAS library will extend the QBLAS capabilities to let you use BLAS functions directly and have an implicit use of multiple GPUs inside this call once you have relinked your application against the GPU-enabled library. It's very simple. You don't even need to recompile your program. Just relink or preload the shared library. Of course, it is usable with many existing applications like Octave, Scilab, etc. Another use case would be k-value pairs sorting. So here we also have good speed up against CPU and accelerated computers. The code which is doing this is essentially the same. We generate the data, we copy data to device, we sort it with just one command, and we transfer back to host. The interfaces used here are similar to STL, because the thrust, which provides the GPU radix sort, is a so-called, is a kind of revised STL library for GPUing. Also, the cool thing that thrust is currently a classic thing. It has been around for several years, and now NVLabs provides a cube library which can improve these numbers even better by a factor of 2.5. Okay, and at the third example I have wave propagation stencil, which is an explicit code of this kind. We have a 3D loop here, and we have some stencil computations in the loop body. Since it is very hard to provide vectorization for this kind of problem, the speed up here is really small. And we also have a large gap here. We don't use Cuda to code our stencil. Instead we use OpenACC, which for programmer means to add only these 3 directives: ACC kernels, ACC loop independent, and again ACC loop independent vector. PGI recently released the new OpenACC compiler, and it turns that it often generates faster code than even handwritten Cuda. The handwritten Cuda that you can write by hand probably in several days. And this is just 3 directives. Okay, so these cases showed us I hope, impressive efficiency. So what makes the GPU application so efficient? So first of all, GPUs are scalar. There is no need to provide vectorization. There is no need to provide any kind of hints that are making really hard time. The GPU task should be partitioned into a significant amount of small parallel tasks, and this number of small parallel tasks must be much larger than what we have on multi-core CPUs, like an order of thousands. Task threads should maintain the balanced use of 2K resources available on GPUs, which are registers and shared memory. Task threads altogether should access consecutive memory addresses, which is called coalescing. This is a very, very important thing. Threads should not use too much divergent branching. So let's see the negative examples of all these properties. So what is the amount of parallel tasks is too small? We have the compute capability, but we use only a very small portion of it, which means that the GPU resources are wasted. It's okay if the number of tasks which we have is larger than the number of tasks we can handle simultaneously on GPUs. This will be handled by the GPU driver. There is no need to worry about that. More not trivial thing is resources imbalance. For instance, we are using tasks for threads which have too much shared memory. If we are consuming too much shared memory, we also will not be able to feed the whole compute capability, because the remaining tasks will have to wait for available shared memory, although free registers, another resource, is available. So everything needs to be in balance, ideally. Maybe the most important thing is about memory, because the memory in organization in GPUs is quite different from CPUs. All memory transactions are 128 bytes. The optimal strategy is to have a warp, a synchronously executed group of 32 threads, to generate a single memory transaction, such that they will subdivide one transaction between the memory requests of individual threads. This is the ideal variant, when everything is aligned and everything is perfect. But it is also possible that this address, this aligned start is shifted. In this case, we will need two transactions. This transaction to load this small part, and second transaction to load the larger part. This is not so bad. The worst case is when each individual thread of warp is generating an individual transaction. What happens here? For instance, this third thread takes the 128-byte transaction and loads only 4 bytes from it. Only 4 bytes, and everything else is wasted. So the memory bandwidth efficiency in this use case is very low, and this case should be avoided as much as possible. Probably someone can name an example of just describe the example of program that leads to such behavior. For instance, we are using multi-dimensional arrays. That could be a good case, and that could be a worst case. Where is the switch? It depends on the array layout and in what order we are accessing the elements. So, for instance, we have a row major array. If this row major array will be accessed as one row here is a consecutive row, and it will be mapped on consecutive work group of threads, we will have this case with one transaction, and everything will be with the top efficiency. But if we will instead iterate our multidimensional array in columns, we will have this case. One element will be taken from every row, and the efficiency will be, I think, terrible in most of the cases. Of course, GPUs have caches, and they try to improve a little bit this worst situation, but still it's essential for GPU computing to restructure your algorithm in such way that the GPU transactions will run with the best possible efficiency. If you have the efficient bandwidth utilization, in almost any case you'll have a good GPU speedup. There could be provided a raw number. For instance, your total GPU bandwidth is 100 and 1,500 gigabytes per second, and the CPU will provide you probably 25. So this speed up of 6 that you will see from your program, if it's written in a good way, you will have at least the speed up of 6 just by dividing the bandwidths. Okay, a less important thing, but still important, is that task threads should not divergent in if-else branching. What does that mean? In Cuda, or in GPU computing in general, the same group of threads is executing the same program. And it may turn that in this program you have if and if-else branching. So in case of plain if branching, with a lot of code here in the body, some threads will run this body, and some threads will just skip it. So in this case, we will just waste the compute resource of that skipping threads. But and this case is not that bad. But if we will have else, and also body with a lot of code. Some threads will execute this body, then they will wait for other threads to generate this body, to execute this body, and vice versa, which means that all threads will stall. Here, the else threads will wait, and here, the if threads will wait. So this is called divergent branching, and this case should be avoided as much as possible. So here we provide only the general introduction. More details about architecture will be in the Cuda programming presentation. And for now, I will conclude with that GPU offer much higher performance on massively parallel computations, as you saw. You can start using GPUs in your application very easily. The seamless integration with MPI and OpenMP programs is possible. Libraries for GPU-enabled libraries often provide fairly efficient performance for many typical computational problems, and the Cuda is only needed if you want something very specific or highly tuned. And GPU efficiency is based on 4 factors. You need to provide sufficient parallelism. You need a balanced use of registers and shared memory. And the very important thing is efficient global memory, GPU global memory utilization, provide coalescing, and to minimize the divergent branching. As the last slide, I would like to mention that in Lugano, there are multiple possibilities to enroll for GPU computing education. An academic way would be the University of Lugano, where we provide a parallel distributed computing lab 1 semester, which runs assignments on GPU clusters and will teach you GPU profiling optimization and in application to scientific case studies. And another way is commercial, where applied parallel computing together with NVIDIA often organizes 3-5 days courses on site with mostly the same topics oriented for customers' needs. If you're interested, please register using this address. And for those people who successfully passed comprehensive practical tests for either academic course or commercial course, there are fancy NVIDIA certificates available. Okay, so see you again on the Cuda Introduction to Cuda session. Thank you.